Hello and welcome to this MCA webinar on extreme environment operation of DC motors. What are the challenges and what is required? Presented to you by Maxon Motor AG. This webinar will be recorded and an email with a link to the recording will be sent to you within the next 24 hours. If you have any questions on the presentation material, please feel free to submit questions via the panel on your right. Questions will be answered as time permits. If your question is not answered, the presenters will follow up with you after the presentation. My name is Kathleen Straight with MCA, and our presenters today are Dr. Kafader and Dr. Phillips with Maxon Motor AG. Dr. Kafader was born in Sarnen, Switzerland, was awarded a physics degree and MBA from the Federal Institute of Technology, ETH Zurich, and a doctorate from the UHA Mulhouse in France. He started his career at the ETH Solid State Physics Department, working on the epitaxy of semiconductor heterostructures, and also attended lectures on general didactics and specialized training for technology education. For more than 15 years, Dr. Kafader has been responsible for technical training at Maxon Motor. In this function, he has presented many training courses and seminars for the Maxon staff and customers, from where resulted a textbook on the selection of high-precision microdrives. Our other presenter is Dr. Robin Phillips, is from the United Kingdom. He holds a Bachelor of Science degree in Mathematics from Bristol University in the UK, as well as a doctorate in Astrophysics from the University of Kent at Canterbury in the UK. He is fluent in both English and German, and Dr. Phillips is the Technical Project Manager and Head of Aerospace Projects at Maxon Motor AG in Switzerland. I want to take a brief moment and thank our sponsors of today's webinar. Maxon Precision Motors is a leading supplier of high-precision drives and systems in the USA. Products include small, high-quality brush and brushless DC motors. These advanced motors range in size from 4 millimeters to 90 millimeters and are available up to 500 watts. Maxon combines electric motors, gears, and DC motor controls into high-precision, intelligent drive systems that can be custom-made to fit the specific needs of customer applications. Maxon helps provide innovative solutions at competitive prices for numerous applications in various markets, such as industrial automation and robotics, medical technology, security technology, instrumentation, and communications. Our other sponsor is Electromate, Maxon Motor's exclusive representative in Canada. Recognized as a premier source for high-performance robotic and mechatronic solutions, Electromate offers AC and DC servo and stepper motors, drives, controls, positioning systems, and robots. Electromate supports customers via an extensive product selection, just-in-time and consignment inventory, dedicated customer service, and technical engineering support. And with that, I'll turn it over to our presenters. Please take it away.
Yeah. Hello, my name is Kafader, and I welcome you on this webinar here on deep fried motors. As you can see, actually, as you know, here we are. It's about extreme environment operation of DC servo motors. So we will talk about the challenges and what needs to be required by these drives. Now, what are extreme operation applications? So some examples are deep hole drilling, where you have operation in oil at high temperature, at high pressure, with vibration and shocks. Another area is ultra-high vacuum applications, where the challenge is, or are the high temperatures during the outgassing before you put it into the high vacuum, and then in the vacuum you want to have a low outgassing level. Or a third application field are space applications, where you have high and low temperatures or in very short periods of time. You have vibrations during launch, and particularly if you have an optic satellite, for example, you also want to have a low outgassing level. Now, how do we organize this webinar? We have split it up in two parts. First, I'll give you a background information on DC motors. We'll talk a little bit about how to select motors, about the key motor parameters which are needed for selection. Then I will tell you a little bit about brush DC motors versus brushless DC motors and how we ended up with this maxon heavy-duty EC motors, where then in the second part Robin will take over and he will tell you about testing of these motors, and with the testing you will see what these motors can really do and what they can support. Okay, let's start with part one, the motor background. When we talk about selection of motors, we have developed, let's say, this systematic selection process consisting of 7 steps. For me, always the most important one is the first step. It's gaining an overview, know what exactly you want to do with your drive, how the situation looks like. In this overview, you also define what are the ambient conditions, how do you want to communicate, you define how should control look like, how accurate it should be a little bit, and of course you also define how the mechanics looks like and how the load should be moved. And then in a next step 2 and 3, you have a closer look then at load, at how the drive looks like, and only once you have done step 1 to 3, you can really go in the details and select the gearhead and motor type for a particular application. Actually, today we will focus a little bit on this here, particularly on step 5 and 6 about motor type and winding selection. At the end, of course, you have to verify that what you want to do from a point of view of control, that it really works, so that you have selected the right sensor and the right control. One way of looking at this is considering the drive system as a black box. This helps quite a lot in the situation analysis. So you see, or you first define what do you want to do, what's the task of your drive, and then you have to make sure that the quality, that the outcome of your task is correct one for what you want to do. You have to also look at power consideration. Is there enough electrical power, current voltage, to do whatever you want to do from a mechanical point of view, mechanical power given as force and velocity, or if you have a rotational load and torque and rotational speed. Today, of course, we will focus a little bit on the green sections here. It's about environment. What is the temperature around the motor? What is the atmosphere? Or is there any vibration? But always think about that also a drive creates emissions, which go in the same way. So a drive also creates heat, makes noise, and in some cases also electromagnetic emissions. When talking about application, essentially at the end what the motor must do is deliver a certain amount of torque at a given speed. And this is our standard diagram, how we represent such operating points of torque and speed. It's the diagram gives you the speed as a function of the torque. Of course, you can also have more than one operating point. For example, a second one would be at a much higher speed, but maybe at a lower torque. Or another operating point could be maintaining a position against an external force like gravity. That would be at speed 0. Or during acceleration, of course, you have a speeding up of your drive, which usually needs more torque to accelerate all the mass inertias. So at the end of this acceleration process, you typically have the highest torque and the highest speed. Now, of course, the first thing you have to consider and to look at is that your motor has high enough speed to cover all the operating points. In this case here, what you can see is that the operating range is limited here by the maximum permissible speed, and it cannot reach this operating point at high speed. You find information about the maximum permissible speed of a motor in the maxon catalog, for example, in line 23, or in the diagram, so this is the limit, the upper limit of the diagram. So speed usually is a simple task to find out. A little bit more complicated are torques. So how big is the torque to accelerate? How large is friction? So there's a little bit more time and effort involved to get all this information. At the end, if you have all these operating points, what you can do is condense them into just essentially 3 values. One value is an average load. It corresponds to the root mean square average over operating cycles. That's essentially the continuous load, or in other words, the motor would heat up in the same way during an operating cycle as if it was driven with this root mean square average load. Another important point is, or two other key values here, that's where we need to be, is the maximum load at the maximum speed, that I call it the extreme operation point, and the amount of time it takes to run the motor at this point here. So from point of view of torque, you have to make sure, here we are, that the continuous operating range expands to higher level than this root mean square average load. So what you need is a motor with a nominal torque which is higher than this root mean square average. Short-term operation can still be higher at a higher torque. Now, where do you find information about this? Is in nominal torque is in line 5 of motor data, and the nominal torque actually is a thermal limit. So operating a motor in a short-term operating range, for example, would result in too high a temperature. And the critical temperature in motors is the winding temperature. A very good example showing you that the limits of continuous operating range has something to do with the temperature and how hot the motor gets is if you look at the heavy-duty motors operating range. Typically, for standard motors, we give such a diagram with the red area corresponding to the continuous operating range. Now, if the ambient is hotter, for example, 100 degree, 150 degree, or 200 centigrades, then you can see that the hotter the ambient is, the less the heat can dissipate, and that's why this border of the continuous operating range is reduced more and more. It's not only the ambient temperature which plays a role, but also how heat is dissipated. For example, in oil you have a much better heat contact to the winding which gets hot. So heat is dissipated much better, and which results in turn that you can have much higher torque when operating such a motor in oil than what you can do in air. So that's exactly the same motor once operating in air and here in oil, and you can see from the scale of the torque M that you can really reach much higher torques when operating in oil. As I've mentioned already, you can run the motor at higher torques, but only a limited amount of time, and the big question is how long is short. Now, it all depends on how fast the most critical part of the motor, that's the winding, heats up. And this is given in line 19 in a number called thermal time constant of the winding, which gives an internal time scale of the heating of the winding. So you can find it here in line 19. For this motor, for example, it's a little bit more than 20 seconds. Now, what does it mean, or how is this diagram to be interpreted? What you can see down here is that you can load the motor up to twice the continuous load quite easily and quite a long time, about 5 times this thermal time constant. For this motor, this would correspond to approximately 100 or more seconds, so almost 2 minutes. So short-term operation can be quite long as the overload is not too high. But you can also see down here that at 3 times the continuous torque, the duration is much shorter than this thermal time constant of the winding. So essentially you see between 2 and 3 times the continuous torque, the time which is allowed is reduced quite a lot. As a rule of thumb, you can say that approximately at 2.5 times the continuous torque, it's this time constant here, that's the duration of how long you can overload your motor. So we've been talking about torque and speed, and how about current? The most important thing you need to know is that motor current is proportional to the produced torque. And there is a proportionality which is given by the torque constant. So essentially it means that for each torque value there is a corresponding current value, and that's why you can draw also in parallel to the torque axis a current axis down here. And you find the necessary information directly here. So for the nominal torque there is a nominal current corresponding and the torque constant here in line 12. What happens if your current is limited? For example, you have a driver with a limited amount of current, let's say a continuous current limit or a short-term current limit, or you have a power supply who has a limited amount of current. Of course, what we've learned, limited current means limited torque. So in our operating range diagram, these areas here are reduced. And for our situation that we have here, it's a big question, how can we accelerate here? Because we don't have enough current to do this acceleration. So probably you will have to accelerate a little bit at a lower rate. Okay, after this introduction about motor data, I'd like to show you the two main construction principles of DC motors. First, the one with brushes. At Maxon we have these what's called Coreless Maxon DC motors, and Coreless means that the winding that you see here has no iron core, so it's a self-supported wire essentially fixed together with some plastics, and this wire rotates, so that's on the rotor part connected to the shaft here, and here we have the commutator where the brushes run on. The magnet which is needed in here is fixed on the flange here, so this is and goes into the winding. The really nice thing about brushed motors, brushed DC motors, is that's the most simple motor to run. All you need is a DC voltage. You connect the battery to the motor and it runs, it turns, and the higher the voltage, the faster it rotates. The other concept, of course, is a brushless DC motor. In the brushless DC motors, you don't have brushes. That's why the winding cannot rotate, so it's on the stator part and is in close contact later to the housing. This has one advantage, is a much better heat dissipation. And the other point is that this time, or on these motors, it's the magnet that are mounted on the shaft and rotate. What you need to drive such a motor typically is some Hall sensors which give information about the position of the magnet, so that at the end you can, with a suitable electronics, drive this motor. And that's maybe a disadvantage of these motors. It's not just a simple battery what you need, but you need a piece of electronics in between. By the way, whether you have a brushless or a brushed motors in a deep hole application, the big question is how do you get the voltage down there? You have to consider that over the long lines you will have quite a high drop in voltage, and you have to consider this when driving the motor and supplying enough voltage. And of course you can hardly place these electronics, standard electronics, at 200 centigrades in oil and wherever you want to operate this. So that's a little bit a tricky thing. But what you could do, for example, is use a motor as a generator. So you can also run it the other way around, rotating the shaft, and then essentially a voltage comes out of a motor. Maybe that could be an option. Now, let me come now close to the end of this first part. I would like to compare a little bit now a brushed DC motor with a brushless design and see what are the critical components for operation in these extreme environments. Of course, what you have in both motors is you have magnets in there. You have to be careful, is the magnet suitable for this high temperature, for example? How is the magnet coating? Will the magnet be, how do you say? oxidize and corrode, corrosion, and so on. That's the word I've been looking for. Very similar things is about plastic adhesives. Do they support the oil? Do they support the chemical environment? The same with high temperature and adhesives and plastics. Then another similar points is in vacuum, low-level outgassing. It's always a question. Lubricants, they gas out a lot. Adhesives gas out a lot. So, but these are problems you have in either type of motor. But what you see here on a brushed motor is that really brushes, you cannot operating in oil. They will not work. Brushes are very sensitive to vibrations and shocks, and the brush life will probably be very, very low, particularly also in vacuum, because for proper operation of brushes you need a little bit of humidity and you need a little bit of air. On the brushless motors, you have to be careful about hall sensor. That's typically a problem at high temperature. Solder joints you have to take special care of, and particularly printed circuit boards also, they have a tendency to gas out in vacuum application. But if you compare the two, then I think you can see it yourself that probably it's much easier to create a brushless, or as we call it, EC motor into a heavy-duty motor. First thing, avoid any glued connections, and that's why our heavy-duty motor essentially have a lot of stainless steel parts, components which are welded together with a laser welding. So this gives a very robust design. Then next thing you have to think about cable insulation, any plastics you're going to use in the winding or in the cable that go into the motor. You also have to think about winding tabs which are fully potted to avoid that they loosen in vibrations. And you also have to think about printed circuit board, make them stronger for high temperature, and also check the hall sensors that they can support the high temperature. And the last point you have to do is encapsulate the magnet so that the magnet never sees the harsh environment, and use a high temperature magnet for the material. Very similar things apply if you want to make a gearhead heavy duty. Again, avoid any adhesives. That's also press fit only will not be very well suited for high vibration. That's again, we use stainless steel components which are laser welded inside and outside the motor. Then if you have an application in oil, we add holes so the oil can flow in and come out and do the lubrication and take away the heat. So this all helps. And of course, to make a gearhead very robust, you have to think about using special planet wheels inside to have a stronger bearing at the outside, to have a larger shaft diameter to make it really, really strong. So these were the steps we made, and now in the second part I pass over the microphone to Robin, and he will tell you about testing of heavy-duty motors.
Okay, so the second part of this presentation is really going to show you a little bit about how we went through the development process for these motors and the kind of testing that we did in order to demonstrate that they really are suitable for the environment that we want to operate them in. So I'll just start off on a couple of components, because effectively that's the level that we would start off in the development process. The first question we had to ask ourselves was, how do we come up with a hall sensor that can be used at these high temperatures? Because as I'm sure most of you are aware, many of the or nearly all of the hall sensors that you get on the market are only rated to slightly over 150 degrees C. Because we have lots of different types of hall sensors here, for our standard range of motors. We decided the best way to approach this, given that we couldn't find any suitably priced 200 degrees C rated temperatures, Hall sensors, was simply to test all of the ones that we have. And we tested about 20 different types and came up with one type that had the best promise at high temperatures. And therefore we ran lifetime tests on those, and that's sort of the original laboratory setup that you see here, where we just had them strapped onto a high temperature resistor, heated them up to 210 degrees C, had a magnet spinning in front of them, and just ran it continuously whilst monitoring the output, so it was powered the whole time. And we had the first failure at over 2,000 hours of operation. And so that was basically how we confirmed that this was the type we were going to use. We get quite a lot of questions about these, and we've now had a total of about 5,000 Hall sensors, I think, of this type go into the field, and none of them have failed in real applications. The rotor, which Urs briefly touched on earlier, where he said that one of the things we do is remove the adhesive from it and encapsulate it. And what we actually do here is we take a solid cylinder magnet and then we shrink a tube over the top of it. And then we take two shaft stubs and push those in from both ends, weld them shut, and then grind them to get everything perfectly concentric. And that's how we then have our fully encapsulated rotor. But what we need to do there is then confirm that all of these joints are going to be suitable for the stresses that they're going to see. So what you're seeing here is what we called our rotor torture test rig, and this just twists it backwards and forwards with 6 Newton meters was the torque rating that we used here, which is factors of 10 more than the motor is capable of delivering. And we did 13 million cycles before abandoning the test. Similarly, because we don't have exactly the same expansion coefficients for the magnets and the housing that we're using, because of course they're different materials, we had to confirm that over the full temperature range we still have the press fit, because otherwise the magnet will rotate inside the housing. And so we first of all performed 10 temperature cycles between minus 55 degrees C and plus 300 degrees C, so that the material has a chance to go into the slightly plastic deformation that it will have at very low temperatures. Did that 10 times, then we heat the whole thing up to 300 degrees C, and then try and forcibly rotate the magnet inside the housing to confirm that the torque required to do that is significantly more than the stall torque of the motor. So that's just 2 examples out of many that I could have shown for the overall testing of the components. Then we move on to testing the complete assembly. So we have a vibration table shaker that's combined with an environment chamber, which is what you're seeing in the bottom right here. The black section underneath is the shaker, and then the components to be tested go inside the environment chamber here. And then we run vertical and horizontal vibration tests at low temperature and at high temperature. Then comes the question, how do we do the testing in oil? And originally we looked into the formal test facilities that you can buy for doing that, and decided they were far too expensive for us at the beginning, when we didn't know whether we were really going to have a market in this area or not. So we started off just simply with standard deep fat fryers, which we filled with hydraulic oil rather than chip pan oil. Modified the circuitry on them to enable us to heat them up beyond what the manufacturers originally wanted, and ran our tests like that. As soon as we'd seen that we were going in the right direction here, we moved on to slightly more sophisticated fryers, running them outside because of the amount of smell we were producing. And only after we'd then demonstrated that we were going to be capable of building motors and that there was actually a market for them did we start to invest in more formal equipment. And we built, this is out the back of our factory, we built a standalone container with fireproof walls in it, with a filtration system on it because we have a farmhouse directly behind us, so we have to be careful that we don't annoy our neighbours with the fumes. We moved on to laboratory heaters. We had this kind of standard configuration to start with, where the motor and gearbox are mounted at the bottom, and then a brake is used to simulate a load on top. And then we started adding different sizes, so these are brakes that are needed for the higher torque, larger motors in the series that we're doing. And basically then there's a bunch of logging equipment in order to be able to obviously collect the data as we're running the tests. And this is sort of the current setup that we have, where there's now 5 of these test rigs in there. We have fairly deep oil baths, different size brakes on top, capable of going up to a couple of 100 Newton meters, which is sized for the maximum torque that you can get out of the gearboxes that in this size range that we produce. And then, of course, all the associated control electronics. I'll pick out a couple of sort of interesting test results that I think are worth mentioning. One is no load current in oil. So the green line represents the current that the motor draws at a particular speed when running in air. And as soon as you, of course, immerse these motors in oil, then you get additional friction drag for the rotation of the rotor internally to the motor. And there's something of a conflict here between an optimal design that in all our standard motors, what we aim for is to have the smallest possible air gap between the rotor and the winding. Because the smaller the air gap, the better the magnetic fields interact between the permanent magnets and the electric magnetic field that we're producing with the winding. And that's how you produce a high power compact motor, is by keeping this gap as small as possible. But of course, if this gap is small and then filled with a viscous fluid, you get a significant amount of extra drag. And then there's 2 factors that come into this. One is the temperature that the oil's at. So the viscosity of the oil decreases as you increase the temperature. So that works in our favor. Then unfortunately, as you increase the pressure, you also increase the viscosity again, so that works against us. So one of the things that you have to be careful when you're trying to lay out your overall design is that you restrict the motor speed and don't let it go to too higher speeds. So that means juggling with the gearbox ratio that you choose. If you have a gearbox in there, this graph looks like the situation is worse, but it's not really, because it's just going to higher speeds. So the vast majority of our applications that we see customers actually using these combinations out are down at the 5 to 10,000 RPM range. But it certainly is an issue that you have to consider when you're sizing out the correct type of motor. Just picking up here a couple of the initial test results that we had. This one's now about 5 years old when we built the first running samples. In a no-load configuration, we were able to put them in the oven at 260 degrees C and run them continuously for several days. Now, we don't actually, if you look at our catalogue, you'll see we don't actually rate them at this temperature. We have a certain amount of margin in there. And we're suggesting a maximum temperature for the winding of 240 degrees C, which lets you place the motors in an ambient temperature of anything up to a little bit over 200 degrees C and still get a 30-degree margin for the winding, which of course then heats up as it does work. So you can still get quite a high power output in a 200 degrees C ambient surrounding. The higher you go, so all the components in the motor are rated to 240 or higher, so you can go all the way up to 235, but then you only have a very small amount of extra heat that you can allow to go into the winding. We've just to demonstrate that the cold temperature starting is not an issue. Also done cold temperature tests. You get as you might expect at minus 70 degrees C, a short burst of high current draw whilst the grease gets moving. But after that, there's no real issues. then the large fraction of our testing over the last few years has gone into lifetime testing at different loads. And especially if you look at the gearbox torque ratings in our catalog, they're normally set out quite conservatively to deliver 1,000-hour life or more lifetimes. We've noticed that there's quite a lot of people who want to use, especially in the oil industry, who want to use motors or compact gearboxes at significantly higher ratings than we would normally give out, but are quite happy with that because they don't need the full lifetime. And so that's what this graph sort of shows, is that a GP22, in this case, a 22mm diameter gearbox, which we would normally rate at somewhere around 3 Newton meters. You can in fact quite happily take it up to 6, 8, 10 or even higher. We've got one customer who actually runs this gearbox at 19 Newton meters. And as long as you're willing to accept that the total operational lifetime drops to below 100 hours, then that works fine. So there's people who move just valves, for example, that has a few second duty cycle, and they want to do that only a few times per cycle that the motor or gearbox is downhole. That works just fine for them. One point that's maybe worth noting, the oil operation that we do, because we don't have a sealed system here the way that most applications in the field would do, the oil gets very dirty and oxidizes, and so we end up with, I think, significantly worse quality oil that we're running in than a real application would do. I thought I'd just show some of the learning experience that we went through during our early development a few years ago. Of course, we didn't get everything right the first time, as might be expected. So the vibration testing showed us that, especially at low temperatures, we had to be careful that the winding taps, if they're not potted the way it's done here, or shown here, the winding taps do break under vibration. The original press fits and welds that we had, the welding wasn't deep enough to provide the strength for the joint at the front. So the solution to the winding tap problem was to pop the winding. So here we've cut open one of the windings, and you can see the way the top section now is filled with adhesive. So the top left here is before it's been filled. There you see the little bits of wire, and after you've potted it, then this is what it looks like, and we cover up all the top section here as well. We then extended that about 3 years ago to potting the entire winding because of issues we were having where the oil was being dragged at high speed over the surface of the winding, and particles in the oil, if it wasn't perfectly clean, were gradually stripping away the insulation on the oil on the winding, eventually leaving blank wires here. So to solve that, we now pot the entire system, including here. So here's the circuit board ends. You can just about still make out the remnants of the taps under there, and this is the bottom end. So the left and right pictures here are basically the same thing before and after potting. This potting, we started off with doing this in a more sort of laboratory style, and are now moving on to having automated machines doing that as we move into more volume production. PCB testing. The standard rules of thumb that you use for laying out how thick a PCB needs to be and how thick the tracks are don't apply when you're running at these high temperatures. So the standard designs that we used had to be adapted, and this is just to show you how we did that. We took the PCBs, we just soldered wire stubs onto them to simulate the winding, and then you pump the rated amount of power through this that you wanted to, monitor it with an IR camera, and based on these results we could then see where the weak spots were in the PCBs and design those weak spots out. We also noticed, as I think many people in the oil industry know, or everybody probably knows, the type of hydraulic oil that you use is key. We didn't have this experience here, so we just started using various different types, some that had been recommended by customers, some that we had suggested ourselves, and we discovered that you can really have a big difference as to how long the exposed parts of the windings or of the electrical system work because the solder is attacked. As you can see, that these are the same solder joints before and after a 700-hour test, I think this was. And you can see the way that the paneling on the left here has eaten away at the solder joint. This was also one of our motivations for then fully potting the system, so that you're basically free as a customer to use whatever kind of oil is good for the rest of your system without the motor constraining that. Another discovery from a few years ago, new for us, but I know not necessarily new for you, was that if you don't leave sufficient gaps between unprotected areas, that you can get carbon build up between them, and this carbon build up then of course starts conducting, and eventually it leads to short circuiting. So again, this has now been dealt with by fully potting this. The soldering standard that we're following is the IPC standard, where we aim for this class 3 standard solder joints as required for extreme environment applications and ones where failure of solder joints can't be accepted. This requires things like new soldering stations where we can also heat with hot nitrogen air, and then we use jigs to also heat up the winding, because otherwise, given the thickness of the winding taps and the thickness of the PCBs that we're having to use here, you can't get enough heat in through a conventional soldering iron alone. This is one of my favorite tests for stressing all the joints. What we do is we take the motor, we run it in air so that there's a minimal cooling here. We attach a flywheel to the front, or basically an inertial mass, and then we switch the motor backwards and forwards between clockwise and anti-clockwise rotation at the maximum speed or duty cycle that we can apply to cause the winding to heat up to 240 degrees C. So this means you're applying tens of amps every couple of seconds to switch the direction of the motor, and of course that causes a huge shock on all the components that are connected together as the torque direction changes. And this plot shows how we ran 3 million cycles before the bearings, in fact, were what caused the failure here in this test. Urs mentioned a couple of other applications that are outside of the oil industry. So one of them is UHV applications. The reason the motors turned out to be suitable for ultra-high vacuum applications is simply because we've got rid of nearly all the plastics. The only adhesive that's still used is to bond the winding and perform the potting. That's all the same type. And of course you can bake that. You can then bake these motors at very high temperatures, so you get rid of any residual material that's on the, or contaminants that's on the stainless steel surfaces. And this gives a plot that shows the before and after bakeouts that was done by one of our customers. And so we have a couple of these running at places like CERN, where really high requirements are needed for the outgassing levels. So just to finish off, a quick summary of what kind of products we now have available. We've built up over the last 4 to 5 years that we've had these on the market. 3 basic sizes: 22 millimeter diameter, 32 millimeter diameter, and a 42 millimeter diameter motor. You can see the approximate air and oil power ratings here. So the largest one is up into the kilowatt range when it's running oil. There's matching gearboxes, so planetary gearboxes, ranging from about 3 to 1 to about 1,000 to 1 ratio. So, and the motors themselves are done in different lengths depending on the amount of power you really need out of them. So this is the 22 millimeter one, longer and a shorter one, and the larger motors we do in 3 sizes: a long, a medium, and a short. The power ratings up here are all for the long versions. Then we also have screw drive models where the gearbox has an integrated either ball screw, metric screw or trapezium screw. So basically this can be any kind of screw type that you define. The key thing to note about this is that the axial bearing is integrated, so the thrust bearing rather is integrated into the gearbox. So it's not just attached through standard rotary bearings, but it's one that's or ball bearings. It's one that can absorb the several thousand newtons of load and still deliver the long lifetime. So the way that's done is you can see in this picture here, the shaft with a screw on it coming in from the left. The final stage of the planetary gearbox is here. There's two standard ball bearings here to do the guiding and radial loads, and the axial bearings here to accept the axial loads, or thrust bearings. I think we've already mentioned a little bit about the applications. The main ones that we've sold the products into so far is the biggest one area is the oil industry, then the next biggest is UHV, and then the two smaller ones at the moment are deep sea submersibles and spacecraft applications. Maybe I'll just show the one example of how we modify this for the motors for the different market segments. This is the deep sea submersible version, where the motor is fully flooded with oil and then sealed after we complete the manufacturing by putting a rotary ball seal on the front of the gearbox. All the holes, of course, are removed, all the joints are welded shut, and on the back we have a sealed connector rather than the wires coming out. This sealed connector, incidentally, is also an option on the standard type. And then finally you have a pressure bladder. This is just a temporary one that's shown in the picture here, so that you can balance the pressure in here with the outside pressure, and the expansion of the oil with temperature has the oil has somewhere to go when it expands. And so this can be placed directly in salt water, and so this is actually the motor running in salt water, and we demonstrated 4 weeks of continuous operation in here before the connector on the back here corroded away, because this the mating connector for the test was not an underwater rated one. So with that, I think we've completed our presentation. So if there's going to be any further questions, I guess we've probably missed the 10 questions I see that have come in here, so maybe we'll just run through those to start with. So the first question is, can you run sensorless brushed motors in a downhole environment? So the answer to that is yes, providing you have a sensorless controller. So we do have customers who do that. Urs was mentioning at the beginning an issue about the voltage drop if you run cables down. So of course there's the majority of downhole tools that I'm aware of run on battery power and high temperature rated electronics. And it's worth pointing out at this point that the electronics that you see in our catalogue, we do not sell for high temperature ratings. We have partners in the oil industry who have more experience at doing high temperature control electronics, and we would just advise you to contact them if you need high temperature electronics. So the sensorless operation is certainly possible. What's the high temperature limit for these motors? So we are saying 240 degrees C for the windings, and therefore the motor itself and the gearbox itself has to be placed in something that's slightly below that, so you can get some useful work out of them. The majority of applications I'm aware of are in the range 180 to 200 degrees C, and that's where we've done most of our testing, because we can't go any higher than that, because the oil, when it's exposed to oxygen, will start smoking above those temperatures. So we've demonstrated it's about 2,500 hours of continuous operation with the rated load on these motors and these gearboxes, so the 3 Newton meters on the 22mm gearbox, for example, in oil, in our test facility, where the oil is at 180 to 185 degrees. So. and there's no failure after 2,500 hours. That's just when we abort the test. So then there's a question on polyamide PCB material. So the question is whether it's because we chose that, whether it's because of its high temperature performance or whether it's mechanical properties. So it's because of the high temperature performance. We have aircraft applications, for example, or spacecraft applications where we use FR4, which is fine for its mechanical capabilities there. It's purely, we switch to polyamide purely for the temperature rising. How much temperature percentage should the values in any maxon motor catalog vary because of the power losses? I'm not sure if I understand that question. So, I mean, all the losses are incorporated in the ratings that we give. So joule losses, for example, or eddy currents, that's all incorporated in the ratings that you see there. So you don't need to worry about any of those in your calculations. And so is the Hall sensor failure rate related to operating time or only time exposed to the high temperature? So it's operating time that we saw the failure after. So when it's continuously being powered and seeing a moving magnetic field in front of it. We have not seen any failures when they're not turned on or when they're not powered on. Although, I mean, admittedly, we've only tested for a few thousand additional hours there. We're using Hall sensors at 260 degrees C. No. The Hall sensors, their signal starts to fade away at about 210 degrees C. They're still just about usable to 220. But anything above that, they don't work. What's the mode of failure of the gearbox? So if you overload them on a short period of time, these standard gearboxes break by usually the pins inside that guide the output stage gears snap off. We've compensated as much as possible for that by using the best steel types that we can, and by putting supporting plates on the back of the output stage so that the pins spread the load out across each gear. But ultimately you're limited by the strength of the material that you're using there. The failure modes over longer term operation, so you're running them for many hours and eventually they fail, it's usually wear on the teeth of the gears. Or on the pins themselves. In air operation, we normally see the pins wearing out first, but because the lubrication is so good when they're in oil, it's generally the teeth themselves. So these HD gearboxes, we change the thickness of the gears as you go towards the output stage, because obviously there's more torque on them there. So and we add additional gears. So the input stage has 3 thin planetary gears on it. Then the second stage would have 3 thick gears on it. And then we move to 4 thick gears. And then the final output stage has doubled up thickness. There's some cutaways I think that we have in our catalogue that sort of show that a bit better if you want to look into that more. Are there any reliability or performance issues with Hall sensors operating, meaning motors starting at less than -40 degrees C? In my experience, they're only rated to -40 based on data sheets. So that's correct. The vast majority of Hall sensors are only rated to -40. We've been through this exercise for very low temperatures for many of our aircraft applications, where we need the motors to be rated at the -55 degrees C mil spec that most commercial aircraft are rated at. And the Hall sensor that we are actually using in here it's the same one that's used for the high temperature. We've extensively qualified, and so have companies like Boeing. Where, like Boeing 787, we have 44 motors per aircraft that have these sensors in them. So there's 44 times 3 sensors in each aircraft. And they've been qualified without any trouble at minus 55 degrees C. And obviously the cycling there that goes on is significantly more than it would be for most oil industry applications, because the aircraft's being cycled every time it flies. Have you considered using fluorinated oils like Krytox? So we spent some time wondering whether we should be recommending an oil for use with these motors. And in the end we decided that wasn't helpful, because so many of our customers put a lot of effort into finding what they consider the perfect oil for the rest of their application. And we therefore decided that we should be concentrating on having the motors capable of running in any oil the customer chooses. So that was the justification for that. What's the melting point of the solder? I believe it's 305 degrees C or 306, something like that. What about leakage across the bearing seals? I guess that was referring to my sealed motor comments. So the standard motors, as we sell them for the oil applications, is they're deliberately open. The bearings are not sealed. There's no covers on them, and that's to encourage the oil to flow through the motor as much as possible, because that aids the cooling. If you're referring to the oil the immersed oil flooded version, the bearings are inside behind the seals. So there's a shaft seal. It's made by Ball Seal. It's a known company for producing rotary shaft seals, and is rated to 1 bar pressure difference between one side and the other. And so the issue of leaking doesn't really arise. What would be the typical modifications needed for a motor to be used in space? So the space industry has a whole different set of requirements. As you may know, Maxon built all of the DC brushed motors that are on the Spirit and Opportunity rovers on Mars, or the MER rovers. And we currently have a big development project running for the European Space Agency's ExoMars rover. So we know a little bit about what has to be done here. And typical examples are the wiring needs to be changed from Teflon to Kapton. The wiring type internally would maybe be different. Some of the materials used we would switch for lower outgassing types. But the biggest differences really are just the sourcing of the material. The space industry for all of its flight hardware wants fully traced material with material certificates to prove that the type of steel that we said we were using in the flange really is the type of steel that was used in the flange. Whereas normally for our standard products, and this includes the HD series, we would be relying on material certifications from our suppliers. For the space applications, we make them deliver proof of measurement of the material that was used. Geothermal logging tools do not usually run off the batteries. Correct. So we also have a project running at the moment that's only in its early stages for running motors with high voltage rated windings. So we've concentrated on the EC32HD to start with, and we have a 600 volts rated winding there. And the idea then is you have a high voltage power supply on the surface, and you just run a very high voltage down your multi-kilometer long wires, and you still have close to 600 volts when it arrives at the motor. The EC22 at the moment, we have a development project with a launch customer for rating it for 225 volts. So if you're interested in this, you can ask about it, but you should be aware that it's not something that's been through lots of field testing yet. It's basically just in the early laboratory testing stage. Is there a minimum RPM for sensorless motors? I think I'll let Urs answer that one. I think we, looks like she's on mute, isn't it?
Yeah. If you run sensorless motors, you need a minimum speed, because sensorless electronics will not, you cannot run it in a real sensorless mode at low speeds. Sensorless motors at low speed will be operated like stepper mode. So the minimum speed typically is about, for these modes, is 500 RPMs and higher, I guess.
The next one is, do you have motor drives that enable you to achieve full motor performance of the largest oil-filled motor? And so the answer to that is no. I think somewhere around about 500 watts is the maximum that our drives are able to do. Does the 4:1 oil-air torque ratio also apply to gearheads?
I think it was the operating range diagram of the motor in oil is about 3 to 4 times higher than the one in air.
Right, so no, the ultimate rating of the gearbox stays about the same. So when the components fail internally, they'll do that at the same rate, the same torque level as whether they're in air or in oil. But what is much better in oil is the lifetime at high loads. So where an air-operated gearbox has to lubricate itself via the grease that's in there, that grease will rapidly crack because of the pressure that's being applied to it when you put a heavy torque on it. And once the grease cracks and it no longer lubricates properly, and then you get wear-related failures within a few hours usually. Whereas that similar kind of load running in oil could run for tens or hundreds of hours. The graph I showed of lifetimes was the oil lifetime. After a motor fails, presumably due to heat, is there much hope in repairing it and reusing it, or is it more common to replace the motor? So our general statement there is our motors are not repairable. They're sealed units, in part because of the amount of welding that we put on them. And in general, they should not be considered repairable. So someone says, I'm using an EC 4-pole 32 brushless 480 watts motor with a 33:1 gearbox. What does it mean of the starting current, which is the 53 amps described in the maxon specifications sheet? So the starting current is in any motor if you don't limit the power draw when you turn it on, will draw the starting current for a fraction of a second, so it's down well below the microsecond level, whilst it speeds up. Because if you consider it for the first nanosecond or so, you have a stationary rotor. You have a stationary rotor, and it has to, and that's effectively the same as a fully stalled motor, and therefore it pulls the stall current to get started. But that drops off extremely rapidly, and of course any real power supply isn't capable of delivering that, or any normal power supply is not capable of delivering that. So the motor doesn't actually start up as fast as it would normally be able to do. And so to some degree that's a bit of an artificial number there. But that's basically the explanation of it.
Yeah, and be aware that the starting current only will be there if you apply the nominal voltage. So if you apply a lower voltage, this current will be lower. If you apply a higher voltage, it will be higher.
Have you measured viscous losses in thinner oils, for example, in low temperature applications? So no, we use one type of oil, and we've got the data we can distribute on the published viscosity of that oil at different temperatures. So effectively, some of those lines that were in that plot, although they're labeled with temperature there, we could also label them with viscosity. And that would then enable you to say, if you selected an oil with a defined by the manufacturer viscosity level, you could predict what the viscous losses would be. And I think that's the last question that's been sent here. So I guess we pass this back to the moderator.
Thank you. Thank you for that informative webinar, and thanks to all the participants today. I also want to thank our sponsors, Maxon Motor AG and Electromate. Just as a reminder, please visit our website, motioncontrolonline.org, where you can find numerous motion control resources, including the webinar recordings from all our past webinars, as well as the upcoming webinar scheduled for the rest of this year. I believe we answered, the presenters were able to answer most of the questions. If any came in since they ended, we will record those and they can get back to you after the webinar ends. And just one more reminder that this webinar has been recorded, and an email with a link to the recording will be sent to you within the next 24 hours. Thank you so much again to our presenters, and thanks everyone for listening. Have a great day.